All right, we're going to do through quick hints for those that are kind of actually doing the homework. We'll make this one I'm not going to call it easy, but once you see the rotation thing, believe it or not, the solving for reactions is just kind of where you start in this stuff. So I'm going to kind of go through conceptually the problems as I remember them here. One of them was, in fact, you had a pin joint here and a roller joint up here at some angle, right? And you had a member or a beam right here, right, kind of running along there, and you're supposed to solve for the reactions. Well, the free body diagram, you had a force pushing down there, which of course this free body diagram converts to this. Reaction, reaction. And then that thing slides down. And what you have is this. You write your sum of the moments about that. This force times distance equals this force times distance. And so then you solve for that. In all reality, you can then conceptually, once you know that, you can do all kinds of different stuff. Try to avoid the habit of just doing some of the forces then, and now instead write your sum of the moments about this point here, which falls that one out of the equation and this one's out of the equation. You know this one, so this force times distance equals this force times distance. You've now solved for this one. Once again, try to more or less go ahead and try to avoid the easy way of just doing some of the forces, and now think about the fact that this force here and this force, they intersect there, right? And so these two forces come out of the equation, and so now this force times distance equals this force times distance. Go back here. So I'm going to do that again on a new sheet. So the fact of just constantly reevaluating about what point you do your sum of the moments is the key to really being effectual or being, very competent and very quickly in terms of using graphics and concept and thinking about rotation almost exclusively. We have a rotation here, we have a pin joint, and we have a roller joint here. This is our beam. We have a known force here. You need to solve for the reaction. So what you do is, again, you show your reactions here, and you just start picking points, right, to write your sum of the moments about. The most logical point to start with is there. Once you do sum of the moments, this force times this distance equals this force times this distance. You can do R cross F. The sum of the moments is what solves it. Now you know this one and you know this one. If you knew those two, you can actually go ahead and now write your sum of the moments about this point. You know this one here, and so now you can know this one here. And once again, you can then take these lines and kind of convert them up here and do it again. And this time you're going to know that this one falls out and this one falls out. This one does not. Your force times distance here equals force times distance here. That's how you go about doing it. And then you check that your sum of the forces in the x equals 0 and the sum of the forces in the y equals 0. Traditionally, how many people will solve that problem immediately is to go ahead and break this up, right? And it's perfectly logical. Break up that force into two components, this way and this way, but that is not the way you want to kind of now learn to solve problems. You want to think about the graphics of moments and torques. And so the way I will be solving these problems in terms of this rotation is force times force times distance, which is the same as force times orthogonal distance, if you would. Force times moment arm, force times orthogonal distance. And once again, it's really about R cross F. And so to get to the point where you do that is even the best of the best. And that is here when you have this problem here. You go ahead and think of it this way, right? There's your reaction here, your reaction there. You slide this one down. That's your radial vector 1, your force vector 1. This is your radial vector 2, your force vector 2. And eventually you can solve things out that way in terms of I, J, and K, or whatever you need to. You kind of need to know the geometry here, which is given in terms of angles, so you can once again think about that in terms of magnitude and direction. All right, that was one problem. I'm going to go to the next one. Not necessarily in order. Problem here was a conceptual problem that once again they've added actually something in. They've got here, I think they've got a cantilever here, right? That problem is solvable by itself. When all of a sudden you add another reaction in here, one or two, it is not solvable with a force something here. It's not solvable until you realize right there you can break this problem up into two problems, and that problem is basically this one here. Force times distance equals force times distance. Once you solve for this force, you now have this concept here of a force out there, which is going to be reacted by a reaction moment here. And so you need to learn to break this up into two problems. The one I talked about in class, I know the third one I don't have a visual memory to, but the concept, the theme of these is that you need to learn to break problems up into smaller problems. I will go to the last one, which I talked about in class, and show you one more time. This one is a little bit, conceptually it's the same problem, but the way that is in the book is that there's actually a couple of cantilevers there. So you got something like there and something like there. You've got a pin joint up here. Remember that is tied to the earth, or fixed if you would. Grounded would be what we call it in Inventor. And we had some general structure that it came down, the beam came something like this, right? It had a force someplace there at some angle. We have to remember that you have to assume this is frictionless, which means that the only force is the normal force. And so what you do is you first solve this problem. Once you do that, you can solve for your reactions here. And once you solve that problem, you can do the equal and opposite reaction to there. So it looks something like this. This first problem, the free body looks something like this. You've got a reaction and a reaction. You've got some sort of load here, which of course you slide down, right, to there. And then you had some force here, which of course you slide up, right? And so you have, in the end, your free body looks something like this. Reaction, 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 and a force. Force times distance, orthogonal distance equals force times distance. Sorry, did that wrong again. R cross F. And go down to the next page. Once you have the solution to the first part of it, you now go to the other problem, which looks something like this. Right, and I can't remember all the individual forces on that, but you had a reaction here and a reaction here. Now you've got basically a couple of forces here, and in addition you have some sort of force there. Once again, you can do it by R cross F, would probably be not a bad way to do it, or force times orthogonal distance. And if you know this force and know this force and you know this force, you can solve for that force. And once you know that force, you can once again do the sum of the moments about here to break this force up into components. Right? You know that this component is going to fall out, and you can get that component there. And so learning how to pick where forces come together is what these four problems are about. That is the first step, is to solve for reactions. The real problem is this. What is the shape? If you remember the first thing you do, the first step is to solve for the reactions. Really, the real first step is to draw the deflected shape, or the deformed shape. And so I'm going to go ahead and just finally, for this one, which is the most interesting one of the lot, but we'll see how these deform as we go into Inventor and start using it as a tool to check our intuition. I'm going to go here, right to there. We're going to go ahead and what does that shape look like deformed? So we're going to do our best to kind of think about, this was like this, and I think that problem was like this. My sense is you had a pin joint there and you had a roller joint there, and what that means is they cannot deflect and they can't move in certain directions. You had a pin joint there with a push. So my general sense is that this would deform something like this. Remember, this is free to move, so this is not going to be affected. This is not going to, of this shape is not going to affect the shape of that, and this one's probably going to look something like that. Thanks for listening. Those are the hints. Put the numbers to it, draft them to scale, and probably then use R cross F as much as you can.